So examples of Sturm-Liouville problems include all of the problems that we've seen already coming from separation of variables, so from the heat equation or the wave equation. But in general, any second-order linear operator is going to have this form, and it can be rewritten in the Sturm-Liouville form, sometimes with the use of an integrating factor. So for example, the Bessel equation, which is standardly written x squared y double prime plus xy prime plus x squared minus nu squared times y equals 0. This can be reformulated as follows, just by sort of regrouping the terms and so forth. The easiest thing to do actually is take the derivative of this one, expand this first derivative here, and then you'll see various things cancel, line up, and give you this one that we have over on the left. Similarly, the Legendre differential equation is 1 minus x squared times y double prime minus 2xy prime plus nu times nu minus 1 times y equals 0. And it can be rewritten very easily as this one because the derivative on the x squared is just 2x, and that gives you this one right here. And the Chebyshev equation, which looks like this one, and the Hermite differential equation, which looks like this one. And if you've heard of the polynomials that go along with these, there are like Legendre polynomials, Chebyshev polynomials, Hermite polynomials, and these are families of orthogonal functions that have a polynomial form. And they have applications in all sorts of different areas of mathematics and physics, from acoustics to number theory, combinatorics, probability. Hermite polynomials pop up in physics, relating stuff between the Schrödinger equation and matrix mechanics. Bessel's equation pops up in the studies of vibrating things with radial symmetry. So for instance, drum heads and so on and so forth, ripples in a circular pond, that kind of thing. Okay, so let's look at a particular example, and we'll consider y double prime plus lambda y equals 0. And let's do this on the unit interval here. And we'll take y prime of 0 to be equal to 0 and y of 1 to be equal to 0. So we have conditions which are Neumann at one end and Dirichlet at the other end. Okay. So let's see. So from this, if we start looking for different eigenvalues, if you take lambda to be negative, then you're going to be looking for functions of the form a cosh x root minus lambda x plus b sinh x root negative lambda. And by substituting in the boundary conditions, you'll find that the only way this can be satisfied is if y is identically equal to 0. So that's a loss. Bust. Nothing good there. Similarly, if you take lambda equal to 0, then you'll be checking a plus bx as your for your eigenfunctions. And the BC's, the boundary conditions there, again, will force you into the situation where y is equal to 0. But if you take lambda to be positive, then you strike gold. And so here we're in the case when we've got a cosine x root lambda plus b sine x root lambda. And so let's see. So we're going to need to evaluate the boundary condition at of y prime. So if I differentiate this guy, I'll have minus a root lambda sine x root lambda and b root lambda cosine x root lambda. So evaluating this one at 0, I have minus a root lambda, and then sine of 0 is 0, and b root lambda, and then cosine of 0 is 1. And so that tells me that b has to equal 1. And so then I know that my y is actually, sorry, I said b equals 1. It's not 1, it's 0. So then that tells me that y looks like a cosine x root lambda. And so when I evaluate this at 1, we have a times cosine of root lambda. Okay, now to get a non-trivial solution, then that means that I need root lambda to be a 0 of the cosine function. And so let's take a look at the cosine function. So it's this one here, and the zeros are the odd multiples of pi over 2. So that tells me that lambda n is going to be 2n plus 1 times pi over 2. Or if you want, you can write this as n plus a half pi. Either way, makes no difference. And then we're going to have the corresponding eigenfunction yn, which will be cosine n plus a half pi x. Whoops, x. Okay, so putting that together, then let's see what we get. So here's what these functions. This is what the functions cosine of n plus a half pi x look like for n equals 1 up to 5. And notice the features that they have. So they're required to have a horizontal tangent at 0, and they all do. And they're also required to pass through 0 at 1, and they all do. So they're going to fit the boundary conditions, and any linear combination of these functions will preserve that property. So any linear combination will have tangent 0 at 0 and value 0 at 1. But you still might ask, if somebody gives you a generic function y, is it possible to build this thing as the as a linear combination or as a generalized Fourier series of these built in terms of these functions? Because we talked earlier about how the sines and the Fourier sine series will work. Those sines are all mutually orthogonal, and they form a complete basis, and also about how the cosines work to give you a cosine series. Those ones also give you an orthogonal basis. But now we've got something different. And so it would be a real drag to try and have to prove that you have a viable basis every time a new problem comes along. And that's where Sturm-Liouville theory comes in. It gives you general criteria under which you can say, yes, actually, we will be able to solve this no matter what.